All right, welcome back, everybody. So this is the third video in our series on the existence and uniqueness theorems proof via Picard iteration. Now, so that we were doing this in general in this video, yeah, and that to a large extent we will be, but it's more that we're going to be glossing over some details, or we're going to be going over some of the messier details of that proof. But in order to really figure out where things get a little trickier, a little hairier, we need to come back to this example that we were working on, where we illustrated what Picard's method looked like. So we're looking at this differential equation, this initial value problem up here, and we wound up showing directly that this had a solution of e to the t squared minus 1, and then we showed through Picard's iteration that we strongly suspect that this guy has a series solution that matches that of the function e to the t squared minus 1. So what we are going to do in this video, we're going to address the remaining question here, which is, oh, come on. Oh, where's my pencil? There we go. Oh, it's an eraser right now. That's what's going on. Okay, we're going to answer this last question down here of, well, is this the only solution to the differential equation? Well, here's where we start to go into the realm of pure math. I mean, we were already pretty destined to get there in this video, but here's how this looks in a more general setting. So our goal here is to show that the phi function that we came up with, phi of t equals e to the t squared minus 1, is the only solution. Wow, only solution? No, the only solution. Come on, only, there we go. Solution to the IDP. All right, and here's the strategy behind this one. Our proof is going to look like this. Suppose that we had another solution. So call this guy psi. So suppose psi is yet another solution to the IVP. Solution to the IVP. Great. So here's what we're going to do. I would like to go ahead and take a look at this difference. Consider phi of t minus psi of t. Right, so this guy would be the difference between these two functions, and what we would hopefully show by the end of this is that phi minus psi is actually the zero function. Because if this difference is equal to 0, that would imply that these two functions are actually the same. Right, phi of t minus psi of t equals the 0 function would imply that psi and phi are the same function. So our goal here is to show that if there is another solution, then this difference is 0. So let's have a look here and see what happens if we consider that difference. So specifically, phi of t minus psi is going to be this integral from 0 to t of 2s. Okay, so first of all, remember, phi and psi both solve this integral equation. So this is f of s, not t. Oh, come on. F of s by phi of s integrated ds. And psi is defined similarly. It has to do the same thing. So it would be supposedly a different fixed point of this integral operator. And we then consider their difference. This would be phi of t minus psi of t, which would be the difference between these two integrals, which is f of s phi of s minus f of s psi of s, because that's right, integrals are linear operators. So we actually know what f looks like in this example, right? In this case, this is a 2s times phi s plus 1, and then we're going to subtract off the same definition on the other side. And I have enough room to write it? Yes, I do. and we integrate, or we collapse this. We factor out the 2s so that we wind up with a cancellation in the 2s's as well, so that we wind up with not another phi, but a psi. There we go. Right, so this is that difference, right? And we can write that in terms of an integral operator. Now, here comes in a fact that we should remember from Calc 2, but I won't hold it against you if you don't remember. Recall that for any function, and it will remember it's an integrable function, so for continuous functions it would be a good collection of functions to work with. Recall that for any function, and we'll call this g of t, we have that the absolute value of g of t dt, right, the absolute value of this integral is bounded by the integral of the absolute value of that function. Why? Well, let me just draw a quick example. So if we had y by t here, and we had a function g that bounces all over the place, and let's say we were going from a to b here, then we're looking for this area under the curve, and we want the absolute value of this guy. As it turns out, the absolute value of g is going to be all positive area, so this won't subtract out what that little red under the t-axis would take out. So yeah, if I take the absolute value of this function, then I'm definitely adding. I'm definitely not detracting any area from this. I very well could be adding area to this integral. So that's why or at least heuristically, that's why that inequality holds. Okay, so we definitely have this, and as we apply this, as we apply this in context, therefore, the absolute value of phi of t minus psi of t is definitely, remember, or from above, this is the absolute value of the integral from 0 to t of 2s phi of s minus psi of s, and finish the absolute value. But our integral is bounded now, or the absolute value of the integral is bounded by the integral of the absolute value. So 2s absolute value, or sorry, 2s times phi of s minus psi of s, absolute value ds. And this guy is equal to what happens when I split this guy across both pieces of the product. Not too shabby if I don't say so myself. That does give us a little bit of progress here. So what we're going to do here, we want to get everything in terms just of that difference, right? We just want to get everything in terms of a difference of phi and psi. That way we can try to bound that piece by something that goes to 0. So let's go ahead and consider a domain where this 2s is not too big. So consider values of t such that the absolute value of t is no bigger than a over 2 for some constant a. And we'll say, yeah, so for some constant a greater than 0. Okay, and we can do that. It's really not too far-fetched here. But we can go ahead and specify whatever constant a we want, and sure, that would show us that 2t then is going to be less than that constant a if we take t small enough. So when we do that, then our difference, phi of t minus psi of t in absolute value, is no greater than what happens here. So the absolute value of 2s, it's bounded by this expression. And this 2s then is going to be no bigger than a. Oh, geez, got to go all the way down here. Whoop. Okay, it's going to be no bigger than the a that we specified, a times phi of s minus psi of s. And I can go ahead and pull that a out. So this is a integral from 0 to t of the absolute value of phi of s minus psi of s, absolute value, integrated ds. Okay, great. Why do I want that? Well, have a look. What happens if I define a new function here? Define u of t equal to this integral of the absolute value of the difference. This is actually, again, this is going to be more of a technical argument here. What happens if I use t equals 0? Consider u of 0 equals, well, this is the integral from 0 to 0 of something, so this is definitely going to be 0. And I claim that u itself actually solves a differential equation. Not the original one that we had, but it solves this interesting, a different differential equation. And we're going to show that u actually integrates up to 0. And specifically, have a look here. Not only is u of 0 equal to 0, but u of t is actually greater than 0. And that would be for all t greater than or equal to 0, right? If I used a negative t, then you would change signs, right? I'd have a smaller number in t, or a number in t that is smaller than 0, and that would flip the sign on us. But for t greater than or equal to 0, u of t is a positive function, or a non-negative function at the very least. Notice what happens here. Consider also that u prime, right, the derivative, it's the derivative of an integral, derivative of 0 to t of phi of s minus psi of s ds. The integral of a derivative, oh scholars of Calc 2, you know that this is just going to be phi of s minus psi of s. Or not s anymore, these are actual, honest to goodness, t's. Whew. But this is exactly what I have for this guy. So actually what I have here is a different, oh wait, do I have that right? Maybe not, okay. Yeah, so this guy, yes, this guy from our estimate above, that's not equal to that guy. It's actually bounded by a times u of t, right? This is bounded by a times the integral from 0 to t of phi minus psi, which is exactly the definition that we took for u. So that means that the derivative of this new function that I've created is bounded by some multiple of the function itself. And that would work provided I can use this a. So that would be for all t. And I don't have to use this 0. I can just go ahead and say for all absolute value of t less than or equal to a over 2. All right, so that means that I have a bound on how quickly this function can grow. Look at what happens here. If I go ahead and subtract a minus, or au from both sides of this inequality, I will have a prime, or u prime of t minus a times u of t is less than or equal to 0. Okay, and that'll be for this, the specified interval for t. We can subtract this guy to the left-hand side, multiply both sides by an integrating factor. So I'm not actually treating this as just an ODE by itself. This is actually an inequality, so I have to be a little bit careful here. Multiply both sides by e to the minus at, and lo and behold, the left-hand side is the product rule on this this product of e to the minus a times t times u. All right, we're okay so far. And I know what you're thinking. Yeah, just go ahead and integrate both sides and you're done, right? No, sorry, we can't do that. This is an inequality, not an equality. for more on this, I will refer you to something called Gronwall's inequality on why you can't just go ahead and integrate from here. But what I do want to point out is that our solution, our function's derivative, has to obey this inequality, or rather, if we tried to integrate both sides here, yeah, I know it says that in the notes here, it's not quite right. So listen to the teacher by not listening to the notes. So bear with me for a second. If this was the case, then I'd have an e to the minus t times a u is less than or equal to, well, in this case it would be a constant. But the constant satisfies this u of 0 equals 0 initial condition, so that we can go ahead and say that this is actually bounded by 0. So in this case, u would be less than 0, and it is also greater than 0, which would imply that u of t actually is the 0 function for all time in that interval. So specifically, that means that phi of t is equal to psi of t for this small, or this arbitrary interval here, minus a over 2 less than t less than a over 2. And this is the flexibility in the epsilon that we had in our gamma, sorry, is that right? In our alpha and beta from the original nonlinear existence and uniqueness theorem, right? So, yeah, because a was arbitrarily chosen, we can take this this a out to however long we want. So a could be a very, very large number, but the point is that this guy, this same inequality is going to hold. Therefore, u will actually have to be 0 over whatever interval of t we want. Therefore, phi and psi are the same function. Okay, so again, that is just what happens for our specific initial value problem. So that right there, that's the end for this particular example, right? We have shown that there is a solution, and what we just did shows that it is unique. Right. So doing this in general, I have to make a few comments here. We have by no means proven the full theorem the theorem in full generality. This is just an example illustrating what you would do in implementing the proof in practice. So if you were to create a more general proof, this is a general outline of how that proof might look. So regarding the existence of each phi sub n, we're really just asking, is each previous iteration of the sequence, or each previous iterate, continuous? And sure, there's no problem there. If I go back up to what Picard says, or what the iteration looks like, we're starting with the 0 function. And that 0 function is continuous. So sure, if I integrate a continuous function, I get a continuously differentiable function, which is still continuous. So that means the next function is going to be continuously differentiable as well, and so on. So every single one of these guys is continuous. But we do have to be a little bit careful, because this f is only defined to be continuous in a small open rectangle. So some iterations might actually eventually lie outside of that rectangle. So we are not guaranteed that each one of these phis actually does exist, because there's a problem with the f, potentially. So in order to fix this, we can restrict t to a smaller interval than what the theorem's conditions say. So instead of looking, instead of looking on the entire interval here, right, this t, absolute value of t less than a, right, instead of looking on that entire interval, we can look to a restriction of that interval. That way we can make sure that we are continuous inside the rectangle at each iteration of Picard's method. But this does limit how, so once we do that, we can establish the existence of an upper bound on f itself, so that we can limit how big the derivative of our solution can be. right? And that would be the thing that would break this theorem, is that our derivative blows up on us, right? And we saw that in the in a previous video talking about what happens when we look at the existence and uniqueness theorem for even for really nicely behaved but nonlinear functions or nonlinear equations. So we just need to make sure that that derivative doesn't blow up and get away from us. Okay, so we can go ahead and make sure that, or the reason why we have to look to a smaller interval for t is so that we don't break the continuity of this f function. And the convergence of this sequence is even worse to consider, because even if you have a sequence of continuous functions, the limit does not have to be continuous. I will say that again. The limit of a sequence of continuous functions need not be continuous. Case in point. If I plot a whole bunch of these kinds of functions, so here is what's happening on a bounded interval from 0 to 1, and I will go to another function, just cutting that in half, but continuing to be 0 from there on out. And then I go down to a quarter and make that 0 until the end. And then I go again, cutting that in half. The point is that these guys, if I number them 1, 2, 3, and 4, I can continue that sequence of functions, all of which are continuous, but the limiting function is a delta spike. So this is actually a discontinuous limit. So even if we wind up with a sequence of continuous functions, the limiting function need not be continuous. So that's an issue of what kind of continuity you're talking about in your in the limit of your sequence of functions. So we're not going to deal with that right now. Just know that it is an issue that you will have to deal with at some point. So I guess that was limit number 3 here. Establishing that the sequence converges is actually a result of either monotone convergence or of the Banach fixed point iteration or fixed point theorem. This is, again, these are topics for advanced calculus for sure. It's way beyond the scope of the class right now. But I wanted to at least show you that this is what differential equations look like once you get beyond this class, that you're looking not for explicit solutions, but rather you're looking for properties of solutions and establishing when these guys exist in the first place. And finally, the question of uniqueness is handled very similarly to what we did in the earlier half of this video. We're just going to have to make sure that we restrict the domain, the t domain, sufficiently small to a sufficiently small interval, and that will make sure that this a, right, this a up here on the right, or makes sure that we can go ahead and solve this this differential inequality. So that is where we're going to go ahead and leave this discussion. It does get very much, it does get nastier from here. So yes, it is an important thing to study. So there are entire course sequences on this kind of subject, and these are classes in real analysis, applied analysis, or things called advanced calculus. Feel free to peruse them at your leisure. They are difficult to look at in the beginning, but the arguments there are ubiquitous and extend into a rather elegant theory for how functions behave in general. So where we go from here, we're moving on to a new chapter. We've done just about everything we can with first order equations, which means we need to bump up the complexity a little bit. We're going to move on to second order equations, and these are a little bit different. The solution technique varies a little bit in this new setting.